Welcome to this presentation entitled Splitting Up Your Work in Chunks. There might have been a time way back then you were a young SQL programmer, you had just started using SQL, but maybe you came from some other language, and you asked someone, I have this table, I need to loop over that, how do I do that? And that person looked at you and smiled and said, no. In SQL, you don't write loops, you write set-based statements. You work with all data at once. And as you progressed with your career with SQL, you come to appreciate that. You come to love those set-based statements. But then every once in a while, maybe you saw a really big table and you thought, should I really work with all that table at once? And maybe you could do that, but maybe also you should split up your work in chunks. This is a slide you have seen quite a few times now during this summit. Still, one thing I like to call out. So PARS has a whole more things to offer than just this summit. And here's one cool thing. This one, this one, this one, and this one, and this one. They are all free. So these four give you possibilities to free training, and this one gives you the chance to engage yourself in PARS, which can be really fun. Session evaluations. This can't just be stressed enough. It's extremely important for PARS, for me, and for all the other speakers to know how we did, what we did wrong, what we could do better. So please, for all the sessions you have been to, make sure you fill in this evaluation, and also please fill in for this one, no matter whether you think I did really great or if I thought did really bad. And you can also win prizes if you submit them by next Friday. So who am I then? Well, my name is Erland Sommarskog. I live in Stockholm, Sweden, where I work as an independent consultant, been an MVP for SQL Server for many years. I'm maintaining my website, Sommarskog.se, which, is a small collection of longer articles. My email address is there at sql@sommarskog.se, where you can reach me if you have any questions that you don't get answered today or come to you after this session. Yes, I should also say that this session is a recording that you're listening to. So while this recording is running, the plan is I will be monitoring the Q&A in the chat window. So I will either answer questions directly in the chat window or take them for the last 50 minutes where we're going to have a live Q&A. So what will I talk about? This is my agenda. I will first start to talk about two scenarios where chunking certainly could come into play. So in here they're labeled a bit cryptically, don't bite off more than you can chew, or be nice to others. I will then talk about implementing chunking, and that's the main meat of this presentation, but performance, pitfalls, things you have to look out for. And the last thing I will discuss is how we could use chunking for error handling. Here cryptically labeled with all or nothing is not what you want. So let's say this, you have a table and you want to perform an operation on that entire table or the better part of it. It could be this, that, there's an integer column in this table and a key column, and you think my business is going to grow really big, so I need to big it. And of course you could use all the table to make that change. But you might decide that, I'd rather create a new version of this table and copy all the data over to the new table. Or it could be that you have added a new column to that table and now you want to initialize that column by taking values, either some constant or taking values from some other table. Or you might want to do a purge operation like, get rid of 50% or 90% or whatever of all the rows in that table. Now say that this table has a size of 300 gigabytes. What could happen if you try to do that as a one single operation? Hey, it could be a lucky day and everything could go just fine. But it's very, very likely that the transaction log file would start to grow violently and maybe even eventually not even fitting on the disk anymore. Temp Table could also be a challenge. Both the data and the log file could grow because you need to fill in temp tables for your operations, or that could be query plans with spool operators, hash builds, sort builds, etc. Another thing to keep in mind is the memory. Maybe your table is a lot bigger than the available RAM in the machine. Now, if the operation only requires a single scan, that's not a big problem because SQL Server will read a row, it will get into the buffer cache, and eventually that row will fall out of the cache again because it needs to fit the new rows. But if SQL Server has to come back repeatedly and read the same row many times, then it will be reading the row every time from disk, and that is not going to be fun. Also, the rollback, consider this, maybe halfway through you realize the operation was wrong or it's taking too long time or something just crashes. Now the rollback also takes a very long time. Now the remedy for all of these problems is to split up the work in chunks. Divide the chunks You work into chunks operating on a subset of the data, not all at once. So it's a combination of those loops you wanted to write as a young kid and the set-based operation. But of course, not one by one, but reasonable amount of rows at the time. The chunk size should of course be small enough to avoid these problems with the log file and temp table, etc. At the same time, this is very important. Don't make your chunks too small because the chunking will add overhead. And the bigger chunks are more efficient as long as you don't hit any of these resource limits. So of course now you're going to ask, so how many rows should I have in my chunk? And you know the answer already. It depends. I mean, first of all, what is the current size of your log file and temp to be? Let's say you already have a 10 terabyte log file. Well, then maybe it's not any problem with that 300 gigabyte table. And also you have to take into account what growth you can permit for the log. But also don't only look at the number of rows. The number of bytes is also very important. Let's say you only have 1 million rows in that table, but there is a lob column that you're going to operate on. You're going to work on that row, on that column. And the average size of that lob is 1 megabyte. You are looking at a 1 terabyte table. In practice, it's a combination of the number of rows and number of bytes, since there is a fixed overhead for the log records, etc. But look at both the rows and the bytes. So, all that this said, I do have a kind of standard value, and that's 5 million rows. I arrived at this value. I was working at a client a couple of years back, and I wanted to change a table, like 45 columns in that table, and by copying the data over to a new version of the schema. And I did some testing on we had a performance server, for performance testing, and I found that when going from 500,000 rows to 5 million rows, I still gained performance by, let's say, 10-15%. I didn't go any further. But as I say here, or as they say, your mileage may vary. Now, don't forget about the transaction log. Even if you do chunking, that alone is not going to save you from issues with the transaction log because you will produce a big amount. Well, if you are in simple recovery, then you might forget about it if you do chunking. But it's very rarely you can have simple recovery in production. And I absolutely advise against putting the database in simple recovery just because you're going to do a large operation. But you may have corruption hiding, and you might regret that if you ever broke the log chain. Don't do that. So, if you are in full recovery, you might have to increase the backup frequency, because if you only, let's say the normal backup scheme is like backing up the log every 15 or 30 minutes, well, your transaction log is going to explode anyway when you do process all of these lots of rows. So you might have to even do as frequently as 1 minute. You may think that, I could add backup log to my chunking script so I get control of it. Yes, you can do that, but only if you write the backups to the same place with the same convention as the scheduled log backup. Because if you write them elsewhere, and if someone then needs to access these logs, it's going to be a problem. So I think the best is just to change the frequency of the job. That's my opinion. Now, so far I've talked about an operation where you more or less have the database and the server to yourself. You're typically operating in a maintenance window to do, installing a new version of the application, etc. Now, this scenario, be nice to others, I'm more thinking here of a small operation, maybe only 5 million rows in total. So it could be actually carried out in a single step. But you are now in a live system and you could impact other users. The operation, if you do it all in one step, it could take up too much CPU, too much memory, and even more importantly, you could cause blocking and or deadlocks. So again, the remedy is to split up the operation in chunks, now with a fairly small chunk size. Now, this means, of course, that your operation will be less efficient, but the overall system health will be better. Now, in this case, again, it depends exactly what you want to avoid. But quite often you want to avoid table and page locks. Let's say this, you're going to implement the purge operation. It's going to work over here on the left side of the table. At the same time, users are mainly reading from the right side of the table. So you don't want to take any locks that blocks these users. Now, you may know that when a SQL Server has more than 5,000 locks on the table, it likes to escalate to table lock. So you want to avoid that. And here is actually a way you can test this. You can run a test operation with different chunk sizes inside a transaction and look and system trial logs, how many logs you actually get. So I would like to show you an example of this. So here I've got a table called BigTrans, and a database called BigDB. We're going to work on this one today. I'm going to talk more about this table later on. So here I'm deleting 2,500 rows, and then I'm looking at system tran logs of, well, what kind of thing am I locking? In what way am I locking it? The ID for it. And if it's a table, I also get the name and how many locks do I have of each type. So I'm going to run this. And we see here, first of all, there's a share log on the database. Then we can see there are 2 key logs on 2 different things, 2 different indexes. Those are exclusive logs. And I got 2,500 of each. So these are row logs. No problem. This hopefully is going to avoid blocking with other users. But we might get worried here because there is also a log on object level, the entire table. Now this is a so-called intent log, which means, hey, I'm down here somewhere doing work. So it's just a placeholder. It will block any user that is going to try to take a shared log on the entire table. Like if someone is trying to do a select count on the entire table, that it will block. And also log on pages, also intent logs. These are usually fine, so you should not be worried about these. Now let's see what happens if I change this number to 3,000. Oh, I got a lot fewer logs this time. Only 1 log on the database and 1 big fat log on the table. So obviously in this particular example, I should stay at 2,500. That's my sweet spot. When you do this exercise, so just to repeat, you should see X logs only on key and read resources. Key or index keys, read are when you have a heap. If you see X logs on object or page, your chunk size is too big. As a matter of fact, if you see X log on page, you might have to look at your where condition, whatever you have, and check that against the indexes, because I would guess SQL Server thinks it doesn't really know how much this is going to hit. So therefore it goes for page logs. Now there's IX logs, and there are a couple of variations of these, SIX logs, etc. But they all tend to end in IX. Intent logs, they are okay. They're only saying I'm in here somewhere. They're not going to block users that only want row logs. Now, let's talk about the challenging of doing chunking. It's not that chunking is a big, wild adventure like going on a multi-day hike. You need overnight equipment. You need food. You need emergency things to get in touch with people. No. But it's not really a walk in the park either. It's like, you could say, it's like a forest walk. You need sturdy shoes. You may have to negotiate a stream or two. You could trip on a branch. You could slip on a stone. So you have to be a little bit careful. First of all, you need to write more code. And that means there is more code that can have bugs. There is more code you need to test. You might need to think about how will this affect the application and the users who see maybe half-cooked data. What you also need to think about this. What if my what if my operation is interrupted halfway through? How can I deal with this? And most of all, performance. If you do it wrong with performance, your chunking operation is going to be worse than if you hadn't done chunking at all. You must do it right. So, and I will talk about these things more or less in the reverse order than they are on this slide. So let's start with performance. Here we have a chunking operation. So what do you think about this one? Is this a good or bad chunking operation? I'm setting the chunk size to 5 million rows, as I mentioned before. I keep looping as long as my row count is equal to this size, and I just do an update top. What I have done here, I've added a new column to this some big table, and I want to initialize it with something. This some value could be a constant. It could also be something that I get from other tables. Now, is this good or bad? Think about that for a second while I get a sip of water. No, I don't think this is a good operation. The first chunk will be fine. It will find 5 million rows immediately where the new column is not. Now, for the next round, it will first have to go through all these 5 million rows, which has been updated. So it will have to scan 10 million rows, and the next one, 50 million rows, etc. And eventually more and more of the table. So it's going to be slow. Unless, of course, there is an index in the new column, but then the update operation will have to pay the price of updating that index, which also will cost a DI. So this is the key. When you're doing chunking, indexing is extremely critical. You must always define your chunks so they go over an indexed column. That is extremely important. If you only don't do chunking. Well, for example, if we take that operation on the previous slide, that's one single scan over the table. That's perfectly okay because that is what we want to do in that case. But now we are repeating this again, all these will be making it longer and longer and longer. So let's say the chunk size is such that we get, well, let's say 500 chunks. Well, in this particular case, that will be equal to 250 scans over the table. It will be a nightmare. It will run for a very long time. So that's very important. Also, I say this, the larger that your chunks are, the more imperative, the more compelling it is to use the clustered index. Because let's say now you go for a chunk size of 5 million rows and you try to use a non-clustered index for your chunks. For instance, by wear condition. The optimizer may look at this and say, wait a minute, 5 million kilocups, that's extremely expensive. I'm going to scan that table, that's a lot better. Or maybe it will go for the index, but still those kilocups are, well, 5 million kilocups, and they're quite expensive. And actually, in this particular case, when we want to work on the entire table, you will never want to access a table by going over a non-clustered index and do kilocups for every row. That's extremely a lot slower than scanning the clustered index once. If you have smaller chunk sizes and only need to operate on a part of the table for your operation, well, then a non-clustered index may work. But again, if you operate on 5 million rows, that's 5 million kilocups. Now, in the end, that might be business logic. For example, well, you're only supposed to operate on the rows which are below a certain date, then you're more or less bound to use the index on that date column. Or you might be joining to other table that could also affect your choice of indexes, and we will see an example of a join thing later on in this session. Now, before I go on to show an example, I'd like to talk about this table called Big Trans. I got this one from Adam Mechanic's blog post about Big Event Works. It has 31 million rows in the size of 2.2 gigabytes, so it's big to be a demo table. It's quite, well, not small, but to be a production table, it's not particularly impressive. But anyway, it has 5 columns. There's a transaction ID, which is integer, and I think my business is going to grow, so I want big in here. I've got a product ID, which is also an integer and a foreign key, and there's 3 more columns that all are nullable for some strange reason, and, well, somewhat funny data types. There's also a non-clustered index or the product ID and transaction date, including the other 2 columns. As a matter of fact, since the transaction ID is implicitly included, because it's the clustered index, this is a second clustered index, so to speak. Now, the operation I want to do this, my chunking task, well, the operation I want to do is this. I want to change the data type of all columns but the product ID and Big Trans. As I said, I want big in for the key, and the other three I think, date time for the transaction ID. Why it's not date, for example? So I first did this with all the table, which means that I had to, well, first drop the non-clustered index, I had to drop the primary key, run 4 alter table, alter column statements, because you can't only alter 1 column at a time, and all of them are rebuilding the table because I'm making such changes. As you might guess, that took quite some time. It took 984 seconds, and the transaction log grew by 20 gigabytes, and I started at 700 megabytes. I'm not going to show you the script, but you can see what I did in this script here if you look at the slides later on. So a better alternative was I created a table called New Trans. With the starting point, I had the clustered index, but not the foreign key and the non-clustered index. And then I did copy all the rows in one single go, and after that I created the foreign key and the non-clustered index. I did it in this order because I found that this was the fastest way to do it. That took 6 to 8 seconds, and now the transaction log only grew by 7 gigabytes. So, can we improve this by doing chunking? Let's see. So here I'd like to introduce you to a generic way to drive chunks. Now the first thing I like to call out is that, well, this is a subprocedure and it takes the chunk size as a parameter. That is actually necessarily not a token of best practice. I ran a whole loads of tests for this session, and for me it was more practical to package these different variations into subprocedures and pass the chunk size as a parameter. I mean, if this was a real-world scenario, you would probably just write a single script, and you might even hard-code the chunk size. All of that is perfectly okay. What is interesting is what's inside this procedure or script. So, I got my min ID and my max ID. Those are the boundaries for my chunk. I start with setting the min ID to the smallest transaction ID in the table. Then they keep on looping as long as I don't have a null value. And then I got this subquery here which says select top at chunk size transaction ID from Big Trans where transaction ID is greater or equal to the min ID ordered by transaction ID. So this will give me all my transaction IDs for my next coming chunk. And then I capture the max value of that one, so I have the boundaries of the chunk. And now I can do my insert saying select from big transfer transaction ID between these two. The last thing I do in the loop is to get the boundary for the next chunk by saying this min query here from big trans where transaction ID is greater than max ID. And of course, if I come to the last chunk, I will get null back. And then I will fall out of the loop, and the last thing I do is to recreate the non-clustered index and the foreign key. Now, before I go on to show you my results, I'd like to dwell on this pattern. Now, in this particular table, the big trans table, the transaction IDs are actually perfectly contiguous. So I could just as well do max IDs equal to min ID plus chunk size minus 1. And you might think that must be a lot more efficient. And yes, for the bigger chunk sizes where I tested this, I gained like 5-10% in performance. Interesting enough, for the smallest chunk size, actually this pattern with top was actually faster for some reason I can't really explain. But the important part is not whether I gain the performance there. Let's say now that actually the IDs are not contiguous. There are big gaps. Well, if there are gaps, I could all of a sudden, if I do the other pattern without just adding, I could get chunks with only 3 rows in it. That's not good. So this is a lot more generic. And not only that, let's say that, oh, this ID would have to be a string, a character thing, or a datetime, or a GUID. Well, this pattern still works. It works on anything you can put an index on. It even works if the transaction ID would be non-unique, at least to some extent, and I will return to that later on. Now, so let's see, how does this what actually did I get out of this? So all the terms you see include restoring the foreign key and the non-trusted index. I kept those values to be in par with your actual operation, but that will sort of dwarf the relation between the numbers a little bit. And we can see here, for the small chunk sizes, I really paid a penalty. Quite a bit. Although we can see sooner how we can actually improve this quite a bit. As long as the chunk size was below 1 million, the transaction log did not grow at all, except for the very smallest chunk size for some reason. I haven't bothered too much to figure out why. And we can see on the execution time, it's not extremely clear because this is still a small table, but 1 million rows is a kind of a sweet spot. It's still 1 second faster than doing 200,000 rows at a time. And at 6 million rows, it starts to get slower again, presumably because the transaction log has to grow. And here we can clearly see that the transaction log growth, that is probably what is taking time from the operation. But keep in mind, this is only 2 gigabyte table. In production, you wouldn't even think about doing chunking if you were going to change the table like this. You would just go all in one bang, boom. Also, very big caveat, this is data from my laptop, captured last year when I first developed this presentation, the first version of it. So if you test this, you could get quite different results. Actually, I ran my test last year on SQL 2016. I reran my test this year on SQL 2016 and 19. And yes, the results were quite a bit different. But I kept these because these are actually more striking. And I will return to that a little bit later on. Now, an important thing here. The optimizer does not know about the values of min ID and max ID. It has no idea at all because it compiles the entire procedural script at once and does not know the value. So it will make a blind assumption about the hit rate, which I believe is 9% of the rows. And if you then are joined into other tables, because it's a little more complex operation that I showed you, that can really affect the performance in a really bad way, because the optimizer may go for a really wrong plan. As a matter of fact, this happened to me a couple of years back. I was working with my client, and I had a table which I wanted to change, add more columns, because I needed those for a calculation. I developed an update script, and I had no problems with performance because in my tested base I had 20,000 rows, no problem. But eventually my client sent it out to their customers, and the customers run it first in the test environment and found that, well, in one place it took 12 hours, at another one I think they gave up after 24 hours. And this time I was not working very much with that client anymore. So, I thought that was not good, but I'm going to deal with this. But before I came around to actually look at it, a guy there, a really sharp guy, said, why don't you try option recompile? Boom, that was it. Now it ran within 20 minutes. Perfect, adequate. But obviously, option recompile for small chunk sizes, that could be quite a bit of an overhead. So if you, let's say, you work with 5 million rows, so that takes, let's say, 30 seconds to process such a chunk. Well, if then it takes 50 milliseconds to compile, that's not the problem. But if it takes 50 milliseconds to compile and 50 milliseconds to process a chunk, now option recompile gives you quite a bit of a penalty. Now, there's another alternative, and that is to push the chunk boundaries, make the chunk boundaries parameter by pushing the whole operation into an inner scope. for instance, an inner procedure. That doesn't sound really fun. Now I need an extra procedure for this. Well, you don't have to do that. You can simply do this. Wrap the operation in dynamic SQL. So, this is not dynamic at all, but I do this so I can make min ID and max ID parameters, so the optimizer can sniff the input parameters and then hopefully make a good plan for the first chunk, which is going to be cached and reused and will be better than the plan for the blind assumption. Now you might say to yourself, okay, for a more complex operation, but this one, look here, there's a clustered index, there's nothing that can go wrong here. The optimizer simply can't, it doesn't need this. This is overkill in this case. Yeah, I thought so too. Look at these numbers. It's a drastic improvement by switching to dynamic SQL. I slashed the execution time with a factor of 3. It's amazing. I don't know what's going on. The plan is actually the same, so it has to be something internally that is not visible in the plan. I don't know. I also gained performance by using optional recompile, but not as much. And you can see that actually for 5,000 rows, it was actually slower than not doing the int at all. I had to pay more for the penalty of recompilation than I gained by getting a better plan. And then, this is a bit problematic for me because you see, even for the bigger chunk size, it's still slower with recompile. But look here, 6 million rows. I think that's 7 chunks in total. It doesn't take 14 seconds to compile these. No, there is actually small difference in the plan in these cases. So the optimizer thinks, I should do this. But unfortunately, that optimization backfires. Now, as I mentioned, I did those tests way back last year, and then I did them this year. My new test this year did not have the same drastic improvement. I think here I landed around 145 milliseconds, and this was actually a few seconds slower, like 105. But there's still a gain with the dynamic SQL, even if not as dramatic as this one. Now, so far this operation, let's now look at the different operation, which is a little more complex. So what I've done here is I've got a table called big orders, and I've added a new column to this one called total amount that I want to set to the total amount for that order. So I initialize it by applying the discount and adding the freight. Whether this is good practice or not can be disputed, but this is just an example. So here I've got to join to this big details table, and both of them have the clustered index on the order ID. So here, there is a case that certainly a possibility of a lot more few plants, or a lot more possibility of plants. And I did this also again with doing chunking, the same pattern as I showed you before. A big orders table has 5.1 million rows and 1 gigabyte in size. And the big details table has 50 million rows and 3.8 gigabyte in size. So let's now look at the results. And here was a surprise for me. All of a sudden, dynamic SQL is a lot slower. What is going on here? I had to scratch my head a little bit before I found out. The reason lies in the statistics. The big trans table, when I work with that one has perfect statistics. They've been sampled with full scan, or updated with full scan. This one has big orders, has sampled statistics, and the lowest ID in the histogram is 13,063. This means when processing the first chunk with IDs between 1 and 1,000, the big orders table, it starts at 1. There are a couple of gaps, but not very many. So the optimizer saw, everything is outside the histogram. I'm going to go for 1 row. And then that plan was good for 1 row, but it was not good for 1,000 rows. Same thing for the chunk size of 5,000. Again, not good because it was processing 5,000 row, but the plan was optimized for 1 row. But once I came as far so that the chunk size at least partly was covered by the histogram, the optimizer made a lot better choice. Now, there is a quite simple way to work around this. I can do an update statistics on the primary key, the clustered index, with full scan. And now you can see the times are a lot better. Maybe not an extreme gain compared to doing nothing at all, but at least I did avoid this problem. And these times include doing update statistics, I should add. Important here, I only did update statistics on the primary key. Don't do it on the entire, let's say, update statistics, big table with full scan. Let's say there's 50 columns in that table and most of them have autostats. That's a full scan for every column. That is going to take a long time. Don't do that. Only for the index where you use it. Now, there's one more thing I like to call out why we actually should use dynamic SQL and safeguards. So I also did this operation on a different set of orders table and details table. where the orders table now has the clustered index on the custom ID and the primary key, the order ID, is non-clustered. Look here now what happens, and I did this both loop chunking over both the custom ID and the order ID. When I don't do anything recompile or dynamic scale, I'm in for a complete disaster for the small chunk sizes. Of course, a chunk size like 1,000 rows at a time, I wouldn't use that, you say, but keep in mind these are small tables. In a real-world table, actually, the smallest chunk size would even be 5 million rows. And you can get this problem. Because that's also what you want to avoid. You may not actually care whether it takes 96 seconds or 96 minutes or 127 seconds or minutes. Both might be okay for you. But you don't want this. You don't want 4,300 or whatever it is, because that's just way a long time. So that's why you should always use dynamic scale or optional recompile to avoid these disasters. In passing, we can look here compare when doing the chunking over the clustered index and the non-clustered index, and we can see, I said previously we should do it over the clustered index, but we can see it's actually slightly better to use the non-clustered index in this case, and that is because we're joined into the details table where the clustered index still is on the order ID. So for the overall query, that was the better choice this time. Now let's talk about multi-column keys. So let's stay at this big details table. It has a primary key on order ID and product ID, and that particular table, there are up to 600 products per order. So, well, what could we do if we're going to do an operation on that one? Do that top loop. Just ignore the product ID? Well, let's say I want a chunk size of 5 million rows. If some chunks have 5 million rows, 600, who cares? No problem. I might not even bother when it's 1,000 or 1,600. I could bother about that, but in many cases, yes, I can do that. Yeah, that's not a big deal. So, and believe me, you want to stick to this pattern as long as you can. Just simply use that top loop, because the alternatives are not really palatable. But of course, let's say that it could be 10,000 products per order, and you must absolutely not exceed 1,000 rows at a time, because then you could start to take table locks. Well, obviously now you need something else. You can't just do that simple top pattern. Well, could we just not extend that to use 2 or more keys? How difficult could that be? Well, let's see. We're going to move into this script, and I'm going to warn you, this might go a little bit too fast-paced for you, but there is a kind of point in that which I will return to. So first of all, I've got update price simple, which is this simple plain loop where I don't care about the product ID. So I just say select min ID. Well, that's all right. Min order ID from big details. Keep on looping as long as that one is not null. Run my select top choice query here, and I will get the max order ID. And now, of course, I could get more than 50,000 or whatever I have in my chunks. My operation here is quite a silly one. I'm just updating the price by 1.2. Yeah, but it's just a test of the chunking as such. Doing that one, I got up to recompile here to buy what I said before, and then I get the min ID as the min order ID, where the order ID is greater than that one. But let's now say I really want to make sure that I stay within my chunk size. Exactly, I don't exceed it ever. So I wrote update price double. And there's a lot more variables here, min order ID and min product ID, and max order ID and max product ID, and also stop order ID and a stop product ID, and a game over. So I get first my starting point, and I can't use min as I need to use top, because of course I want the lowest order ID and the lowest product ID on that order. So I run a select top query, and I also want the last order, the highest order ID and the highest product ID on that order. So run another select top with order ID desk and product ID desk. I keep on looping as long as it's not game over. I initiate, in the beginning of the loop, I set these two, max and product, to null. And again, I run my subquery, the select top chunk size, that will get all the order and product IDs for this chunk by saying, okay, from this my starting point, and remember at this point, yeah, so bigger than my starting point, and then all the remaining orders. So this will qualify a number of rows. Then I want to see what is the highest one. I can't use max here because again, I want the correlation. I want the last order in my chunk and the highest product ID in that order. So I use row number, and then I say, okay, well, the row number is equal to chunk size. That is the one I want. Now, for the last chunk, this condition will not hit in rows, and that will leave these variables unassigned. Oh, rather, they will not be set to null. They will retain their values, and that's why I have to set them to null up here. Now, once I get my chunk, I need to consider that there are quite a few cases. First of all, I need to say I did not get anything back at all. Well, then I need to say this. I need to set the max ID to my last product. and also say the game is over. So anyway, I got a few cases here to cover. So first of all, did I move to a new order? Yeah, if I did, well, then I need to consider all the remaining products on that order, all the orders that are in between, and also the first couple of products on that last order. So I got this update with a where condition with these all conditions, which are maybe more. That's not really nice, isn't it? And also not free compile. And then there's also the possibility that I'm staying within the same order and only update the products within this range. Once I've done that, I need to look for the end. If I'm not having game over, I need to look for the starting point rather on the next chunk. So ORID equals max ORID and etc. to get the one that comes after this one. Now, when I tested this, I found that performance was not very good. And the reason for this are the optimizer does not do a good job here. The plan is not good. So I found I could resolve this. I had to write update price triple. Well, the logic is the same. The difference is that this update statement now is split up in 3 different ones, and this one runs faster. Now, as I said, this might have been too fast-paced for you, and if it was, well, you have kind of got to my point. I don't like this code. I think it's too complex. I mean, this was only 2 keys. Just imagine if you have 3 or 4 keys, it would only get worse and worse and worse. So I don't like this. I would like to look for alternatives. So let's do that. So this is what I like to call the big temp table. And the small temp table, we'll look at that one later. This is a quite simple-minded solution. What I do here is I create a table called hash chunks, and I've got the ORID and the product ID and the chunk number, and the clustered index with the chunk number as the leading key and the other 2 there. Then I get all the keys from the table into this table, and I compute the chunk number by taking the row number, -1, integer division by the chunk size. The reason for -1 is, well, then that all chunks have the same size but the last one. It's not very important in this case, but that we will have one towards then where it really matters with having -1. So that's why I'm sticking to it. Now, then what I do, I set up a cursor over all the distinct chunk numbers in this loop. Keep on looping over that cursor as long as I get a chunk number. And then I do my update here, setting the unit price to, well, unit price times 1.2, and doing this access subquery for doing the update on this chunk. Now, observe one thing here. When I set up this table, I have the clustered index on chunk, now ORID, product ID, and the same thing when I numbered them. So this means that every chunk is a contiguous set of order and products. So this join is operating on a contiguous set or an adjacent set of rows in this table. SQL Server has quite a few optimizations for this case. I also did a test where I didn't care about the order, so each chunks would have rows that would scattered all over the table like this. And the performance was like, well, I don't remember exactly, but I think like 3 times slower. So this was a better way to do it. So again, yes, each chunk has a contiguous set of keys for an efficient join. But obviously, yes, this is slower. Compared to the triple top loop, in my test, it was between 1.3 to 5.6 times slower than the triple top loop. The one that was really slow, like 5.6, I think in that case, it did not go for the best plan for that chunk size. So maybe it could have been improved with a hint. But obviously, we are sacrificing efficiency for simplicity. There's no denial about that. Yes, this is just a simple way to do it. So I talked about the big temp table and the small temp table. This was the big one. And yes, it has as many rows as the actual table, but the temp table is a lot narrower. So if the big table has, let's say, 100 columns, well, this one is a lot smaller. But of course, it would still take space in temp DB. And of course, it requires a full scan of the table. And let's say we have it's a live system and there are writers to that table. Then we will block these writers when we're doing this scan. So that may not be very good. So this is not always a good solution, but I'd still like to show it because I still think it's a viable technique. Because it's simple. There are situations where this is good enough. But nevertheless, there's also the small temp table, where we fill up one chunk at a time. Although it is a little more complex, but it's easily enough. So this one, I renamed the variables a little bit because they work a little bit different. I got a current order ID and a last product ID, and I have a row count which is equal to the chunk size initially. My temp table is my order ID and my product ID only, no chunk number this time. I initialize current order ID to be below the lowest order ID in the table. So my current order ID when I start is nothing at all, so to speak. And I keep on looping as long as my row count is equal to the chunk size. I start with truncating the table, whereas of course it is empty already, but so I could do that at the end of the loop. I always like to initialize variables, etc. and tables at the beginning of loops. Then I fill it up with all the orders and products for this chunk. Again, I select top chunk size query, and here I go for order ID equals order ID and product greater than the last product ID, because these are the boundaries for the previous chunk. And for the first chunk, well, there is nothing in this one, or everything is order ID is greater than current chunk. So that's the condition. So this one will be a little more complex if you have 3 keys, etc. And then I capture the row count, so I know whether I got a full chunk or not. And then I do my update. It's the same thing as before. The keys in the temp table defines adjacent set of rows in the table, so it will be efficient. And then the last thing I do is I will get what was the upper boundary for my chunk. So I get the highest order ID and the highest product ID on that order by doing this top one order by descending query. When I tested this compared to the triple top loop, it was between 1.3 to 3 times slower. And compared to the big temp table, it was, well, sometimes even as fast as 0.2, but sometimes actually slower. And I like to stress for all of these examples, if you try this on table on your own, the profile of that table is going to matter a whole lot, so you can see quite different results, but I would expect the patterns to be, well, more about the same. Before I leave this, I should say the script that I show you has full procedures for, well, these show you a few more examples and also some performance data from my original tests. Or did I update them? I don't even remember. But anyway, I did update them. That I did. But anyway, I got some performance data there just to look at. But you should try this on your own because it depends quite a bit on the table. Now let's leave performance and discuss about the application impact. If you don't do chunking at all, well, everything's one transaction. And the application and the users will see, well, neither none of that operation or the final result of it. Unless, God forbid, you're using no-log. But no, you don't do that, do you? But now if you introduce chunking, now you have to ask yourself, how will the application behave? And moreover, how will the user behave if they see data that's only been processed halfway through? How will they react? And this is even more pronounced if the operation is interrupted, accidentally, on purpose, because you could have an operation that you know has to run for a couple of days. And because you can only run it at a few hours at night. You need to think about this. Well, it could be that you can just shrug your shoulders. You've added a new column to a table. You're not exposing it anywhere. No problem. But it could also be that you may have to make substantial changes to the applications. This is particularly true if you have one monolithic operation today and you decide, oh, I want to break this up in chunks so it can be more efficient because it's causing a lot of problems. But you need to have to think, how will that affect users and the application? I can't give you the answers, but you need to think about it. Now let's talk about resuming chunking. So you run your chunking operation, then something happens. The server crashes, or you have decided to actually restart. So how are you going to deal with that? And I like to discuss this by looking at four canonical operations, not 5, 4. So the first one is a purge operation. Actually, the first one I like, before I go, this is one more technique to do chunking. So from this big trans table, I want to delete data that is older than purge date. You may recall that there is no index on the transaction date column, or no, where the transaction date is a leading column, I should say. So if I would do chunking with something like just delete top rows, I would have this problem again, scanning more and more rows. So what I do here is I get all these rows, transaction ID, compute the chunk size, but now I only want the chunk boundaries. So rather than saving them to temp table, I only save the min and max, and then I set up a static cursor over all of those and loop over that cursor. So then I can simply just do these delete. Now, the question was about resuming chunking. What do I do if this operation is interrupted for some reason? Well, not a big problem. I can just restart. What has been deleted has been deleted. No problem. Now here we have this insert operation. We're copying data from big trans to new trans. Let's say now that this operation is interrupted halfway through. Can I restart? Just don't worry about it. No. It's going to fail fatally directly with a primary key violation because it will start from the beginning and try to copy a row that is already new trans. But it's very easy to address because I can do this. I can set min ID to isNull. First try to look, is there some data already new trans and get the max trans ID. And then I can restart. Of course, if someone would insert data into new trans, well, there is a stop, I would have a problem, but I would have a problem anyway. And then I can keep on looping. Update absolute. This is the scenario I've added a new column to my table. So here I've added a new column called new column to big details. I'm looping over it. And here is just some value, but it could be taken from some other table. Now, if this one crashes halfway through, can I restart? Yes, I can. There will be no harm as long as assuming that this some values is not taken from any other rows in the table. So it will be the same value every time. But obviously, I would redo a lot of work. I would go through all these chunks again. I can improve this somewhat by adding this condition, and new call is null. So I don't have to restart and redo all these updates, but I would still have to go through all these chunks. So I can make it a little faster by starting with saying, okay, I will start finding out where was I. So I set the min ID to min order ID where new call is null. So I can speed it up a little bit. And then we have this update price simple, where I'm setting the price multiplying by 1.2. So if this one crashes halfway through, what do I do now? Think about that for a second while I have a sip of water. Yeah, I only have one choice, restore back up. I mean, how would you be able to tell which prices that have been updated or not? So clearly we need something better. We need to plan ahead. So here is update price resumable. So when I enter it the first time, it will see that, okay, there is no table called guest.last ID. So it will create that table. That's a one row, one column table. And I will insert into that the smallest order ID in big details table -1. And then when I come here, I just take the min ID, last ID plus 1 from that table. I do my top loop, the same pattern as before, except that it's a transaction. I save the max ID into this table. Now, if I'm interrupted for some reason and I start, I will just pick up that one from where I was and keep on looping. And at the end, I will drop that table. Now, you might ask, what's guest dot? Oh, well, the guest schema is there in every database. Because I think this is a kind of a temporary table, so I don't want it in the DBO schema. But it's a kind of a temporary table. It cannot be in Temp Table because it must survive server restarts. So then I put it aside in the guest schema. But it could be me that it's just being too fancy. You might prefer to put it elsewhere. That's okay. And you might even want, if you do this operation repeatedly, of course, you might want to make it a permanent table. Now, let's go back and look at some of the other things here. So this update price absolute. Now, let's say I've added this column to my table and you need to initialize it. But I know that my system is so busy, I can only run this procedure between 2 and 3 o'clock in the morning. So it's going to take 8-9 days before I'm completed. And this scanner could take 5 minutes. So maybe then I could shave off those 5 minutes for each start by saving where I was in that help table in the same way. And maybe then it completes in 8 days rather than 9 days. Same thing for this purge operation. So, yeah, it's interrupted. Well, I will have to redo this scan and start the cursor. That is kind of lost. And if I know that I will have to do this, well, then maybe I should save those IDs into some, kind of permanent table. And so if I restart and there is data on that table, I will work from that table, and only then I will set up the cursor again in case purge data has changed from the previous call to find more chunks to delete. So, to summarize, one strategy for resuming chunking is just ignore and just start over. That works very well with purchase and also absolute updates, but then in that case you will redo work. There could be logic in your operation so that you easily can find out where you were. For instance, finding the last row you inserted. Or you can add a help table to track where you were, not in Temp Table but somewhere else. But the thing here is you need to have a plan. If you know that you will interrupt your operation because it's only going to run a few hours at night, you need to code for it. If it's a one-off operation, well, then maybe you don't need to code for it, but you only need to have a strategy. You need to have an idea what's going to happen, because else you will end up here, restored back up. And now I showed you 4 simple operations, canonical operations, but in the real world, your operation may be a lot more complex. Maybe you're calling a stop procedure that you don't really know what it does. And the more complex the operation is, the more likely it is that you will not be able to tell whether you will actually process the row or not unless you tracked it. So you really need to plan ahead to avoid this. Now let's talk for a while for the risk for bugs. I mean, chunking is not that extremely difficult, but it is increased complexity. And if you're sitting at the keyboard coding like half asleep, like this, that you could, make silly mistakes like skipping a row between chunks, or process the same row in 2 chunks, or miss the last 2 rows, etc., etc. So I recommend this. Test on a small data set with different chunk sizes. So you got the logic right. Make sure that you have a test case where the last chunk is full minus 1, the last chunk is exactly full, or just a single row, these variations. Because yes, I showed you a generic pattern, but I know you will deviate from that pattern every once in a while, because it will make sense in that particular situation. Review your code, have someone else to review it, and if possible, add assertions. So if you're copying rows to a table, well, check, do I really get the same number of rows in the new table as in the old one? And performance, you need to test for performance as well. But this is really, really, really a challenge. Because if you have a 300 gigabyte table and I don't know, 10 terabyte database, that is extremely difficult to do because there's so many variations. You can't test all these variations. And when I tested this, I restored it back up every time. And basically, you have to do that so you know that you have the same starting point. And that's going to take a lot of time. You will more or less have to make a choice how to do this from gut feeling. But you need to test that gut feeling and then have to improve it if it's not good enough. But keep this in mind. In many of these cases, you're not looking for the very best performance. You want to stay clear of the complete disasters. And also, don't forget this, should not only look at the execution time, you also need to monitor how much do my transaction log grow, how much does my temp table grow, and maybe also the database itself if you have some sort of version storing, or particularly the accelerated data recovery. That could also matter. Now, the last thing I'd like to talk about is how we could use chunking for error handling. So sometimes all or nothing is what we want. What do I mean by that? Well, normally these update statements, or insert, or whatever they are set-based. They work all or nothing. That's the concept. But let's say this. We are reading orders from a file, 45,000 orders, for example. And that could be errors with some of these orders. That could be that some important or mandatory information is missing. That could be that there is a product we no longer have, or a customer we have blacklisted. So we don't want to accept those orders. But we still want all the other ones. So we can't just do process all in one, bang, boom, because some of them may fail. So do we need to have to process them one at a time? No, we don't need to. We can do chunking. We can divide the orders into chunks. And if one chunk fails, well, we trap that error, redivide that chunk into smaller chunks, and then try again. And eventually, we'll process a few orders one by one, but not all 45,000. So let's have a look at this. So the first script is, well, that's a one-by-one processing. I got a table called new orders where there are 45,000 orders, and there's also a table called new details. I'm going to start this script when I talk about it. I capture the start time, how long I've been running, the row count, the order ID of my variable, and also my cursor that I set up. I'm using a cursor variable here if you haven't seen this. So I do my loop, picking up the order ID, do my transaction, insert into big orders and to big details, commit it, trap any error, a row back, and get the error message. In this case, I'm doing a race error of the error. Normally, I would log that to a table because if a race error that could be trapped by the caller in a catch block. That would be bad. I want the operation to continue, but I do here for the sake of the demo. I look at my row count here. I'll see how many rows are then completed. Let's go back to the script, and I print out. This is a race error with level 0 with no weight because I wanted to see how far it's been progressing. And we can now see, and at the end here, I delete all the rows I inserted. So let's see how long time did it take. And it took, well, half a minute, 31 seconds. Let's see if we can improve that by doing, let's see, the wrong place. Sorry about that. There are the slides. So let's go back to this one. So here I'm doing chunking. I don't have the order ID. I have still the start time, how long I've been running. I got the chunk number. I got a temp table. This is a big temp table. That is, I got an order ID and a chunk number. And the clustered index again with the chunk number as the leading key. Always when you do chunking with a temp table, you always like to have the chunk number as the leading key and the order ID. And then I have temp orders table. I fill up, or again, row number -1 divided by 10,000. I have hard-coded the chunk size in this case from new orders. And I keep on looping, and no cursor here because I will add chunks. I will keep on looping over the temp orders table. I will get the next chunk, select chunk node from temp orders. And you might note here also that this while block is entire, I got a try catch on the entire while block. Do my transaction, And, well, if everything went fine, I'm printing out the diagnostics I processed. This one, again, level 0, but with no weight, so I get the output while the script is running. And I delete that chunk. Now, if there is an error with the chunk, I come down here, I roll back the transaction. I get the current size of the chunk, doing this. Now, if the chunk size is still greater than 1, I like to redivide this chunk by dividing by, in this case, by 100. So I also print out a diagnostic message. And then I compute the new chunk size as, first of all, I compute the node size up here. I missed that, sorry. So I take the chunk size, minus 1, into division by 100 plus 1. I need to do this minus 1 and plus 1, because else I could get a new chunk size of 0. That's really bad. So here, again, I'm computing my chunk numbers, row number, order by order ID, minus 1 divided by the new chunk size. And here I really need the minus 1, because new chunk size could be 1. And then, of course, I can't have 1 up here. That would be really not good at all. So then I have the CT, and then you might think I need to join this CT back to the temp table to do the update. No, you don't need to do that. You can do the update directly on the CT. You might not have seen this before, and yes, it does look scary the first time you see it, or at least I thought it looked scary, but it's really efficient. So I can say this chunk number, set it to the temp chunk, and then add the max chunk number right now in the table plus 1. And if there was an error, the chunk size was, well, this order is bad, and I raise an error in this case. And then I delete it from the temp orders table. So then let's now run this and look at the output. And the first chunk would find this one had errors, this one had errors. Again, this was fine, then one had errors. And now I'm running chunks with 100 at a time. And we can scroll down. There's quite a few of these, and you can see them redividing again. So this means there was an error. There are in total 4 orders with errors in this demo. And then eventually we should see chunks with 50 in them. And yes, it has completed. So let's go down to the end. And it took 10 seconds. And we can just see here for the fun of it, there was one error towards the end. It took 10 seconds to run, so it was an improvement with a factor of 3. Now, when doing this, there is one challenge, and that is to pick the initial chunk size. How do we do that? How to find that value? And that is kind of a challenge. Now, because think of this. If you set the chunk size too high, this means that about every chunk you process will have an error, a row back. That would not be efficient. So here's a kind of rule of thumb, and this is not based by science and not based by any mathematics, just some sort of common sense. So I suggest this. If you expect one row out of n to error out, well, set the initial chunk size to n divided by 10. Of course, assuming that there are no other limitations, like being nice to others, etc. Now, how to determine that then, that might require some good gut feeling. Of course, if you already have a process in place, which is doing one by one, then you can probably get some data from that process of how common errors are. But else you will just have to stick a finger in the air and think, yep, I could do this. Maybe one out of a million, maybe 1 out of 1,000. And then you would redivide the chunks. I would suggest doing that by 100 or 1,000 at a time. So don't do by 10. I think that would be too much. Maybe the last chunk size before 1 should be 10. I don't know. You have to find out and test yourself for your case. One thing also I'd like to point out you should consider is whether the error comes in burst or if they are scattered. Because it could be that once there is one source, when it's produced an error, it produces a lot of them. So if they come in bursts, well, then you might be possible for you to have bigger chunk sizes than they're completely random. So I'm going towards the end of this session, so I like to do a summary. So chunking. This is obvious, as you understand, this is nothing you do every day. It's a trick in your toolbox for the really large operations, to keep the transaction log and Temp to be checked, and to avoid conflicts with the rest of the system. And make sure, particularly when you're doing these really large operations, that you have the transaction log backups running frequently, more frequently than normally, because else the log is going to explode. And indexing is very critical. Your chunking must always follow an index, preferably the clustered index. Repeating scans again and again and again is extremely costly. The top method that I showed you is a very generic way to drive the chunks. It works with any data type you can put an index on. And you can even use it if the leading key of the index is not unique. It's still going to work. And if you have a multi-column key, well, only care about that second level if you really have to. Because defining chunks in a temp table, well, that's less efficient than extending the top loop, but it's so much simpler. But of course, you could have a situation where you really must go for that top loop, but be really, really careful, because that's what I think is difficult. And don't forget about the optimizer. The optimizer should preferably, if you use interval variables, they should always be known to the optimizer, either through option recompile or sniffable by dynamic skill. And if you use dynamic skill, you might have to use up the statistic with full scan on the index you're using, not the entire table, only the index. And don't forget to consider how applications might be affected by you doing chunking, and users, what they think if they see partially processed data. You may have to deal with that. Design your loops so you can restart where they were interrupted. You may not have to code for it, but you at least have to plan for it. And you might have to create a help table to track where you were. And don't forget to test for correctness and for performance. Again, I'd like to remind you about the session evaluations. They're extremely important for me and for PARS. Please fill this in so I know how I did and that PARS know how I did. So that was all. I got one more thing to say. So I've been talking for an hour. I've basically only scratched at the surface on this topic. There's a lot more to discover for you and for me. I made some quite interesting observations when I was running tests for this session. So, this is nothing we do every day. So how could we know everything beforehand? There's a whole lot more things to discover. And if you find something interesting, please drop me a line on my email address. Please do that. So slides and scripts, they are available on my website, sommarskog.se/present. They're also on the PARS website. And the BigDB database, you can get it here on my website. It's 3 gigabytes in size for the download. It will expand to 20 gigabytes and you need at least SQL 2016. So we will now continue with the live Q&A, and this ends the recording. Thank you very much for listening.